Hello everybody, this is Kamcev from University of Michigan. In this short video, I'm going to highlight our recent work published in Nature Chemical Engineering on the topic of lithium-magnesium ion separations with negatively charged membranes. If you want to read the paper, you can scan the QR code. If you don't have access to this journal, feel free to email me for a copy. The conventional process of lithium extraction from naturally occurring brines is evaporation ponds coupled with chemical precipitation. One of the main challenges of this approach is the significant amounts of magnesium ions in these brines, oftentimes at much higher concentrations than lithium, and this complicates the separation due to the chemical similarity of lithium and magnesium. Essentially, lithium extraction from brines that contain magnesium to lithium ratios that are greater than 10 is unfeasible with the conventional approach. And so this has motivated an enormous amount of interest in lithium-magnesium separations, particularly using membrane-based technologies. Most of the work on lithium-magnesium separation with polymer membranes is focused on nanofiltration and electrodialysis. Both of these technologies rely on the principle of size exclusion and charge exclusion by the membranes. Essentially, hydrated magnesium ions are larger and more densely charged than hydrated lithium ions. And so most people have focused on developing positively charged membranes because these membranes are expected to reject magnesium ions more so than lithium ions. If we look at the literature-reported lithium-magnesium selectivity values for electrodialysis and nanofiltration membranes that are tested with either real brines or model brine solutions, we'll find that most of these selectivities are actually relatively modest or low. The issue with these conventional approaches is that polymer membranes tend to have very broad free volume distributions, and so the principle of size exclusion is not very effective with these types of materials. And furthermore, when you do these experiments with real brines, the extremely high salinities of these brines can screen out the electrostatics, thereby diminishing the charge exclusion principle as well. In this study, we investigated negatively charged membranes and concentration gradient-driven transport across the membranes as the basis for separation. This study essentially got started from an unexpected result that we observed in the lab when we tested mixed ion transport across a negatively charged membrane in a diffusion cell. In this type of experiment, we found that lithium ions can readily permeate across the membrane, so the concentration in the receiver cell increases versus time, whereas the magnesium concentration was essentially undetectable throughout this experiment. This suggests essentially an infinite lithium to magnesium selectivity, and this is not something that we expected from a negatively charged membrane, which is expected to permeate magnesium ions faster than lithium ions. And this is indeed the case if you do single salt diffusion experiments across the same membrane. We did some control experiments where we had single magnesium chloride or lithium chloride transport across the membrane, and in this case we do find that magnesium chloride permeates faster than lithium chloride. We also did some control experiments with electric field driven transport, and also in this case we found that magnesium ions permeate faster than lithium ions. And so our previous observation means that the high lithium-magnesium selectivity is only observed when you have a concentration gradient and also mixed salt solutions. To better understand what's happening in our concentration gradient-driven experiments, we have to turn to the fundamentals of transport in these membranes. The mechanism for transport involves partitioning at the membrane solution interface and subsequent diffusion across the membrane. When you have a concentration gradient as the driving force, the ions that partition into the membrane have to be electroneutral. So for every anion or chloride ion that sorbs into the membrane, there has to be a sodium ion or a magnesium ion or a counterion that sorbs with it. These ions then diffuse as a single entity across the membrane to maintain electroneutrality. And so for concentration-driven experiments, we talk about a salt diffusion rather than an ion diffusion. We can describe the salt flux across the membrane using Fick's law, and one can easily show that for highly charged membranes, the diffusion coefficient of salt in the membrane is actually equal to the diffusion coefficient of the coions, or the negatively charged ions in this case. So the key takeaway here is that concentration gradient-driven transport in charged membranes is governed by the minority species. In this case, it's the chloride ions and the cations that balance them. In the next few slides, I'll show that there are two key phenomena that are responsible for the high lithium-magnesium selectivity that we observed during concentration gradient-driven transport. First, there's an unequal distribution of counterions within the membrane. The coions that are responsible for concentration gradient-driven transport are primarily balanced by lithium counterions. It turns out that the magnesium counterions prefer to balance the fixed charge groups along the polymer backbone, and so they cannot exit the membrane unless replaced with another ion. Secondly, we saw that there's likely uphill transport happening for magnesium ions, so they can transport from the low concentration side to the high concentration side under certain conditions, and these two effects combine to give the exceptional lithium-magnesium selectivity that we observed earlier. To investigate this partitioning effect, we performed ion partitioning experiments that can decouple the different counterion populations in the membrane. The key results are shown in the plot here, which shows the lithium equivalent fraction in the membrane versus the lithium equivalent fraction in solution alongside the parity line. If we look at the results for the counterions that balance the fixed charge groups, you'll find that they lie below the parity line. And so this means that the fixed charge groups have a preference for magnesium ions over lithium ions. On the other hand, if we look at the counterions that balance the coions, there's an exceptionally strong preference for lithium ions. And to give you some numbers, at a lithium equivalent fraction in solution of about 0.3, the lithium equivalent fraction in the membrane for the coions is close to 1. So there's an exceptionally strong preference for lithium ions to move with the coions that govern concentration-driven transport. To explain the concept of uphill transport, I'll bring up another equilibrium curve, but in this case I'll show the magnesium equivalent fraction in the membrane and in the solution. This plot shows experimental results for 3 different experiments that were performed at different total salt concentrations from 1 molar to about 0.05 molar. The key takeaway here is that as the concentration of salt in the solution decreases, the preference for magnesium sorption by the membrane strongly increases. And so what does this mean for our permeation experiments? Well, here we start with pure water in the receiver cell at the beginning of the experiment, but as salt permeates across the membrane, this turns into a very low concentrated salt solution. And so the preference for magnesium ions at the receiver side of the membrane can be exceptionally high, so much so that it can reverse the internal concentration gradient, such that magnesium ions transport from the low concentration side to the high concentration side, and this is uphill transport. As the salt concentration in the receiver cell increases, eventually we expect the concentration gradient within the membrane to reverse and align with the external concentration gradient, and thus there's no longer uphill transport. To test the potential for uphill transport in our system, we performed a modified permeation experiment, where instead of starting with DI water in the receiver cell, we started with an equimolar lithium magnesium chloride mixture at a different total salt concentration. For lithium transport across the membrane, we saw that the lithium concentration in the receiver cell increased as a function of time, which is expected from normal Fickian diffusion. However, when we look at the magnesium concentration, we found a decrease in the receiver cell as a function of time, particularly at low total salt concentrations, which implies that there is indeed uphill transport of magnesium ions against their concentration gradient. We also developed an ion transport model based on the Nernst-Planck equation. I won't discuss it in this presentation, but you can read it in the manuscript. This model agrees well with the experimental uphill transport results as shown here. For the last part of our study, we tested this separation process in a more practical system, where we used the model Atacama brine as our feed solution, and we used the flowing electrodialysis stack with only negatively charged membranes and without the application of an electric field. In these experiments, we found that the monovalent ions readily permeate across the membrane, but the divalent ions are largely rejected, just like in our more controlled experiments. We can calculate separation factors of the monovalent ions with respect to magnesium, and we found that initially these values are greater than about 5 or 6,000, and then they decrease as a function of time. And this decrease is largely because the magnesium transport becomes faster as that concentration gradient within the membrane shifts. Nevertheless, these results demonstrate that this process can achieve exceptionally high separation factors under realistic brine conditions, and these values are substantially higher than those of typical nanofiltration or electrodialysis experiments at comparable conditions. I'll end this video with a couple of words on the advantages and disadvantages of this approach. One of the key advantages is the exceptionally high monovalent divalent separation factors, especially considering that we used realistic brines in the final experiments. Another advantage is the low energy consumption of concentration-driven processes, because the driving force for transport in this case is natural. Although this process will likely have to be combined with another technology like reverse osmosis, the separation is essentially low energy. The disadvantages are low lithium throughput. In this study, we used relatively thick electrodialysis membranes, and so the fluxes were quite low. Here, one can think about designing exceptionally thin membranes, for example, like the thin film composites that are used in reverse osmosis to deal with low lithium flux challenges. Another disadvantage is the low recovery of the process. This is intrinsic, and we essentially have to maintain a large concentration gradient to have a reasonable flux across the membrane, but also to maintain the high selectivities. We still have to do quite a lot of process modeling and techno-economic analysis to truly evaluate the potential of this. So with that, I hope you enjoyed this short video and learning a little bit about some of our recent work.